Hello, everyone. Welcome to the final day of the 3-day online training on MEMS design and simulation using IntelliSuite, hosted by CMC Microsystems. So in today's training, the day 3, Dr. Raja will focus on macro model simulation capabilities of IntelliSuite. He'll also show us how IntelliSuite can be linked with other EDA tools like Cadence for system-level integration of MEMS devices. Today's session will be of shorter duration and it will end at 2 p.m. Eastern Time. We'll have a 10-minute break at halfway mark. Please feel free to write your questions in the chat at any time during the training. A link to a short training survey must have been emailed to you by now, and it will also be posted in the chat. Please take a few minutes to fill it up during the break or after today's session. And the survey will help CMC in gathering participants' feedback on the effectiveness of the training and allow us in identifying areas of improvement for future training programs. So following the training, CMC will offer the complete IntelliSuite software package to its academic subscribers for a 6-month trial period. And access to this CAD tool will be made available in the coming few days. So please watch out for your email, and we'll inform all the participants through email when the tool is available to download. Users of the tool will be requested to submit a feedback usage report close to the end of the trial period, and CMC will provide an easy to complete usage report template. So we encourage all of you to complete the report when you use the tool with your valuable feedback, as this usage report will assist us in providing the complete IntelliSuite package on a continuous basis. We understand that you might have questions during this trial period since this was a software demo training, but the purpose of this training was to showcase IntelliSuite features which can greatly help researchers to shorten their MEMS design to prototyping time. And Dr. Shripad Raja presented in great detail how using IntelliSuite can reduce the resources spent on device microfabrication, which can save significant time and cost to the users of the tool. The recordings for this training will be available in the coming few days on our YouTube channel as well. So in case you would need to revisit to look back at any detail that was shared during the training, please feel free to do that. Now I would like to invite Dr. Shripad Raja once again to guide us through the final day of the training. And Dr. Raja, the floor is yours. Thank you.
Yes, thank you, Suraj. Yeah, let me share my screen. Since I just out of one other meeting, I've closed all the modules. I'm trying to open them.
Sure, no problem.
Are you able to see my screen?
Yes.
Yes, okay, great. Okay, so welcome to day 3 of the training. Here we will focus on how to do a system level simulation of MEMS devices. So if we look back what we have done yesterday and day before yesterday is that we explored the software for the multiphysics simulation on day 1, and on day 2 we explored this tool from the clean room perspective. Okay, so once we design the MEMS device, either using the CAD model, which is the solid model, or the process driven model, either way, we have to do a multiphysics simulation. If we are in the plan or if we are trying to build a MEMS device, we obviously have to do a multiphysics simulation. It's only that the design approach is different. One is the CAD model approach, another is the process driven approach. Assume that we are good to go with the fabricating the device. So then we try to use the software tools for optimizing the process recipe. Now let's assume that we are at a stage that our MEMS device is optimized and it is throwing up the signal that is required. So we have optimized and we have finalized the design. So now who let me put it this way. If I have the sensor and sensor throwing up the output, there should be some fellow who has to process the signal and put it in the readable format. And who has to do that? And someone has to do it, and that's what we call it as ROIC, readout integrated circuit. So typically for any beginner, I would just compare this like we have 5 sense organs and the brain is the one which takes which tells us how to process the signal. So either one fails, then it's of no use. So it's the same analogy. Looks here's silly, but that's the analogy that I would like to give in this case. The output of the sensor has to be made readable through ASIC. Okay, ASIC or ASIC is a too complicated term. Okay, let's technically too complicated. Let's use the word called ROIC. Okay, and for ROIC, a readout integrated circuit, if we have to do it, there are 2 ways of doing it. We fabricate the MEMS device and using the wire bond, we can give the feed to the discrete component level circuit. Okay, discrete component level circuit also. Another option is to build the circuit using the standard PDK methods using 180 nanometer, any other PDK like TSMC, Samsung, the GPDK, whichever the PDK. So what we have done in the past is we have tried the 2 options. How do we analyze the MEMS device so that the integration with the circuit is also possible? Okay, so this is what we will explore it today. For this to happen, we will have to understand the working of the device. So now we are at a stage that this device, the working model, the working principle of the device is well understood and it is optimized. We are at that stage. Let's assume that we are at that stage. Now we'll have to create those HDL files, hardware description language files, for us to integrate with other EDA tools, or within the software we have a module called Simple where we can do a system level simulation also. Let's explore that. So before we do that, let me give you an example here. What you're seeing right now is a 2-plate device which represents a capacitive type of a pressure sensor. Let me scale this. Okay, so here the boundaries are fixed in this location. Yes, so the boundaries are fixed in these locations and the pressure is applied on the top surface. Oh, probably in this case it's different, I guess. Oh, it's a dynamic simulation. Sorry. Yeah, so here we have applied the pressure on the top surface and we have applied voltage also to measure the capacitance. Okay, for us to perform the simulation of a system level simulation, or to perform a system level simulation, what we do is we do a macro model extraction. Okay, so in the case of macro model extraction, we have many other macro model extraction based simulation where it is spring constant, rigid body variables, squeezed film damping variables, capacitance. So in the case of HDL file, in the process of creating a HDL file to do a system level simulation, we either choose mechanical reduced ordered modeling or electromechanical reduced ordered modeling. In the case of in the case of devices like pure mechanical devices like the resonator uh, kind of a device, then we generally perform mechanical reduced ordered modeling. In the case of uh, electrostatic force that is applied, we perform electromechanical reduced ordered model simulation. So what do we do here? First of all, remember that any device have to go through three types of simulation. One is static, another is frequency, another is dynamic. So in the case of static, what we understand is for input, what is the output? So if we are giving one input value and what is the corresponding output value, so it is more of a constant input and a discrete output that we get. In the case of frequency, we identify the modes of vibration, and in the case of electromechanical based simulation, then we also do the buckling effect and things like that. I mean, let's park that aside. So fundamental purpose of running the frequency analysis is to identify natural frequency of different modes of vibration. Now comes as the third one, which is called the dynamic simulation. Dynamic simulation is basically a time-based response or a frequency-based response. Typically, it will be a time-based response because we need to know how fast or how slow the device responds to the stimuli that we give. So the input load that we give based on the boundary conditions that we set and the load that we set. So how far is how quick or how slow the device would respond. So we would have already completed the three simulations, that is static, frequency and dynamic analysis, and would have reached a stage that we have a fair understanding of our device working. And now this is where we are at a stage where we do the model contribution. So in the case of electromechanical reduced ordered model simulation, we do the model contribution in the first place. And in the model contribution, we either select small or we select large displacement. If the input load is pure electrostatic force, then we use small displacement analysis. In case if there are loads which are linked to mechanical like pressure, acceleration, then we use large displacement analysis. Okay, either of the two. And the iteration number should be minimum 100 and accuracy is 0.001, or if you want further accuracy, you can always add to this. And how many modes of vibration? So 3 modes by default. You can also reduce it to 2 if you wish to, but 3 modes of vibration is quite obvious. Okay, and typically the mode 1 vibration is always our fundamental mode. Okay, so now at this stage, what we do, we apply and then click OK. Then material properties we have already defined in day 1. We just click select the entity, the material database opens up, we just import it, select OK, and then we assign it. Material properties are assigned. Here, damping definition. So since we are working with mode numbers, the model contribution, so 3 modes of vibration, we generally recommend to give a damping factor which can be editable, which is editable. Okay, so by default, I'm just retaining 0.001. Then I go to loads, voltage. So for this, the voltage has already been defined. Voltage entity for one, I think, let me check how much its value. So one is 0, another is 500. I mean, probably this is for the simulation, I guess. Yeah. So once that is done, we fix the boundary conditions, and then we mesh the design, and we perform the analysis, start to extract macro model. Okay. So you may notice that whatever the selection that we do here is the one that gets enabled here. Okay. So I'm not going to click this because macro model simulation takes a minimum of the model contribution itself would take at least 45 to 50 minutes of simulation. I'm not going to do that, but I'll give you a flow of what we do later. Okay. Once the model contribution is the simulation is complete, we go to results and then we click on model contribution. Model contribution gives us the dominant mode, which is typically the primary mode, the dominant mode, and we try to disable the other 2 modes. Okay. I can even share a document related to this. Probably once you get the access to the software, you always have the access to this documentation. There is a procedure of how to do all of these simulation in the document also, which is what I'm following now. Okay, you can as well do that. Then once we have that, once we complete that, then we redo the simulation in the same flow. We don't exit the module. Instead, we will say scale factor for mode 1. So what is the scale factor? The scale factor would have generated in model contribution. So that value is entered here. So with that, what the simulation will do is it calculates the strain energy versus model amplitudes. Okay, and this is for mode 1. Similarly for mode 2, mode 3, you can set the value. So let me show you. For mode 1, if the scale factor is say 0.1 and increment number can be 10. So for mode 2, I can set 0.2. So I can set these values based on the model contribution that has been extracted. Okay. Then I repeat start extract macro model again. Once that is done, we again go to macro model. Then we take the strain energy model amplitudes data, and then we study the output of it. Next comes as the mutual capacitance versus model amplitudes, because this is an electromechanical based simulation. Mutual capacitance is always a part of it. So we select that and then redo the simulation again. Once that is done, we go to macro model, then we check the mutual capacitance versus model amplitudes. Once we complete all these 3 simulations, we are good to go ahead with system integration. System integration meaning that I am connecting this pressure sensor device to a circuit. Okay, how do I do that? Here, definitely it is not possible. Instead, what I do is all the three set of simulations would have created three files to me. Sorry, not this. So curr.macro model, which contains the full information of the model, the design, the load, the boundary conditions, the stress profile, the and the structural parameters, whatever is associated to that, will be saved in a file called curr.macromodel. So we take these files out from the simulation directory, and then we take another file called macmodel.out. Macmodel.out contains the following information. Let me open this with Notepad. I can show you that. So the node of interest. For me, the node of interest is the center point in this case. In this case, the node of interest is the center point, so which gives the maximum displacement. And we have str.out. And in this, we have the information of boundary condition fixed to one phase, phase 1. These are the two other phases, and with voltage entity. Okay. So this should have been 500, but yeah. Okay. So we have these information here. Okay. So here, once we have these files, we copy them to a different location. Why? Because once we exit the module, go to File, Clean Up and Exit, all the files that are generated during the simulation would have erased. Before we do that, we pull these three files and then copy it into a different folder. If we miss out, then we may have to redo the whole simulation again. Okay. Yeah. So once that is done, we come to a stage where we open up a module called Simple. SYNPLE. So this is a module where we can perform system level simulation. Before we go to system level simulation, let me introduce this module. This module is a system level simulation tool where there are different elements like the ADC, digital elements, electrical elements to create circuits and integrate with MEMS devices. Okay, and we have general elements. General elements is something like a comparator, control, discrete filter. So basically, if we have to do a signal synthesis, we get all of these elements on the table for us to create a signal conditioning system. Okay, so logic, math circuits which can perform mathematical operations. Okay, so yeah, and we also have MEMS elements. We have 1D elements, force, balance, mass, spring, mass, and damper, 1D elements, and we have the beams which can be used to connect or using these elements itself, we can make MEMS devices. So I will come to that stage a little later. So let me not miss out the flow of system integration. Okay, so this is the purpose of Simple, where you can do element-based modeling of MEMS devices. You can also integrate that with electronic circuits. Okay, so now we have completed macro model simulation, and now what we do is we just pull out a template called macro model template. So we have macro model template TED, macro model 3, macro model 4, macro model 4 plus. So what are these macro model? Macro model is basically a black box where we load the ROM macro model file onto this file, which is the macro model file that is created. It is this one. Once we load this file onto this black box is similar to this device now. Okay, when we perform the simulation there, so the output that is thrown by this device in FEM simulation, the same output will be thrown by this template, macro model template. Okay, and we have multiple mode, macro model 3, macro model 4, 4 plus. It all depends on the nodes of interest. In the case that I have chosen, the node of interest, node, not the mode, NODE. So the node of interest is only one. So if it is 1 to 3 or 3 node of interest where it shows maximum displacement, then we choose macro model 2. If the node of interest is beyond 3, then we choose a macro model 3 element. So similarly, we choose a macro model bigger template with whenever the nodes of interest is more than 5. Okay, in this case it's only 1, so we have taken this macro model. So I repeat, this is a black box where I need to load the macro model file onto this black box now. Okay, so for this I already have the file. Let me open this. So here, this is a layout. This is a black box where I load ROM macro model. Let me browse this. So I select and then click OK. Yes. Okay. So it's showing me a warning where it's a post-process dump data will not be generated because it is not an element-based model. It's a macro model simulation. Okay, fine. So now this element is equivalent to this device now. And for that, I connect a DC 5 volts just to run the simulation. Here, a DC simulation. So I can perform DC simulation, that is static analysis. AC simulation is frequency analysis. TRN, transient, is dynamic analysis. Okay, we can redo the whole simulation again, just to ensure that the output given by FEM is matching the output here. So the simulation output that throws up in this module is pretty quick. It takes less than a minute. Okay, so we have X1, So for the X1, Y1, Z1. So what are these X1, Y1 and Z1? So here, oh sorry. So here, oh, not this. We had selected the signals. X1 is the nomenclature we have defined. X1 is X displacement, Y displacement, and Z displacement. Okay. And we have two nodes of interest, I guess, in this. So we have Z1 and Z2. So here we can select the signal. Further, we can connect this to other EDA tools as well. Sorry, the other circuit part of it also. We can replace the DC signal. This is the bias signal, and we can add a general pulse of duration of 1 microsecond to another. So we have, let me go back. Yeah, so we have value 1, that is 0. It links to the pressure that is applied, and the value 2 and value 3. So here the time duration, the pulse 1 should be for 1 microsecond, pulse 2 T2 should be for 3 microsecond. So that is what we are trying to do, and this is a time based signal that we are giving. Hence we perform a transient based simulation where the end time of the simulation is 10 microsecond and the time step for it is 20 nanoseconds, and the signals that we want is what we can check. So if we want to know what is the signal that is coming in here, we have to check this box. In this case it is checked, so whichever the box that we check is what the output that we get. So let's run the simulation. So we have N3. This is what we have given it as an input now. Okay. For which there is a output. So here, how do we read this? X1, Y1, Z1. It is somewhere in, say, yeah, exponential -7. So first decimal point of a micrometer scale. So what is this? When there is a pulse that is applied, let me try to compare with this. So now look at this. So now when there is a pulse that is applied, there is a response from the device. So usually there is always a cycle time, settling time for any device. When we apply any force or any stimuli, there is always a response time and a stabilization time. So with the response time, stabilization time is what we saw. And with the 3 microsecond, we pulled out the force and it has fallen down. And there also there is a settling time. Okay, so this is how we read the signals here. So here we can perform all these analysis, transient, frequency, and dynamic analysis. Okay, and further, if you wish to connect. So a circuit level kind of a signal conditioning system, you can always connect. So this is a case where this imitates the pressure sensor device, and this is a balanced demodulator circuit which is connected to the device. Okay, so these are some uh, simulations that can be performed on system level simulation section of IntelliSuite software. Okay, and these are purely macro model based, which is a equivalent of I would say equivalent of an FEM. A Lagrangian model is created, and then we integrate this with outside electronic circuits. Okay, so any question at this point of time? If there are any question, please drop it in the chat box. Okay, so let me go ahead. You are free to drop your questions whenever you have them. Okay, so further, I'm a researcher where, let me position myself that I am a researcher where I want to build a ROIC using a 180 nanometer technology based ROIC. If that is the case, then I'll not be able to use simple module at all, because I cannot support 180 nanometer technology or the PDK here. Instead, for in such situations, what we recommend is to use a module called EDA linker. In EDA linker, we can convert TEM electromechanical macro model conversion. We browse this file. So we are going to the same location. Sorry, system model. Yeah. We initialize the same file which we actually loaded onto this model, and then we convert that file to an equivalent HDL file. You want to convert this MEMS device file to a VHDL file or a Verilog A file or a PSpice, HSpice, Simulink, Spectre HDL. So you can do that. So here, whether it's VHDL, Verilog, so you can always use Synopsys, Cadence, Mentor if you are a user of it. Let's take the Verilog, and then I would say CPS, capacitive pressure sensor, and then click OK. Then save this file, CPS, on the desktop. Finish. Let me go to my desktop. I have created test.cps. I open this in Notepad, and here is my code. From here is my Verilog A code of my MEMS pressure sensor device. And this contains not just the sensor, the output of the sensor also, the material properties, the type of output in the form of Verilog A code. Okay, so what we do here, since I do not have access to Cadence or Synopsys, what we as from users, what I've learned is in the case of Verilog, we open Cadence Virtuoso and then create an empty file and then paste this code into that empty file, and then a template gets created in Cadence Virtuoso, and further the integration with IC can happen. Same thing is with other EDA tools as well. Okay, so you can convert this to a Verilog A code, or you can convert it to whichever the file format that you wish to. Oops, let's again come back. VHDL, test, CPS, next. Yeah, so CPS. So here, yes, so CPS.VHDL is created for me. So this is a VHDL code. So we just remove this. Okay. We just use it from this location, the VHDL code. So based on the user's comfort level, people use VHDL or Verilog A code. And this is how we do the system level simulation. Okay, either within the software, IntelliSuite with discrete components like this, or if you wish to do with a nanometer scale, then you can convert this to a equivalent file and then take it outside. Okay. So any questions here?
None in the chat so far.
Okay. Okay. We good to go. Okay. Yeah. So this is the system level simulation file. So now let me also show you some of the files that using the element based models that we can create MEMS devices using this module. Sorry. Yes. So here we have MEMS elements. In MEMS elements, what we have is the beams, the comb structures, and plates, joints. Using this, we can connect them like a circuit in this way, and then we can design the device. This is a tuning fork gyroscope. So let me show you how this looks. This is a plate just connected. I can show you the equivalent mask of this. I can convert from here to the layout file directly. And this is how it is. So this is what you are seeing here. So I can perform element-based model simulation. So here what we do is a tuning fork gyroscope where the oscillation happens in the X direction, okay, in the horizontal direction, whenever there is a yeah, the gyroscope. So angular velocity is measured due to the Coriolis force. And this simulation can be performed in this module. And how do we take care of my dimensions? I take care here. The unit length, unit width, number of holes, joint offset. So these are some element based features that we can set based on our requirement. How do I get to know what is what? We go to help and then we have elements documentation. In elements documentation, we have plates, rigid plate, and this plate has so many connections. And what are the input pins? What is unit length? What is unit width? Is all explained. So based on that, we can set the values. Okay.
Siripat, I have
Yes.
a question here. So how we
Yeah.
set the number of capacitors like the COM drives?
In this case, okay. In this case, we use this combs. You have finger number. In this case, it is 28.
But in the GDS, it's more than that. Or is it 20 at all? Yeah. They are
Let
28.
me count. So element, which element is this? I think it's comb drive 1 port 2. Drive 1 port 2. Yeah, so finger number is number of fingers of the comb drive. So it must be pairs, I guess. So let me count 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Yeah, a little more than 28. Yes, what you said is right.
We are counting as a pair, both
Pair, yes.
fixed and movable.
Yes.
Yeah, I
Okay,
think
and
so. Yeah.
and just for one site, one port.
One port, yes.
Yeah. Okay.
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 So here we have this. So if I increase, let me show you. If I increase it to 35, save this. The numbers increases.
But it doesn't adjust the anchor point for the fingers.
Yeah, because for me to do that, I'll have to further adjust the width of the element, the comb drives.
Okay.
Yeah, so I need to position it in such a way that I require 35 number of fingers, for which I need to reduce my line width, the gap between them. So I need to play with these numbers.
But the approach you would suggest would be to design it in the blueprint and then use that number here, right?
Yes.
Rather than going the other way around.
Exactly. Exactly. So I'll close this.
Or I think the other way around would be easy if you just do the schematic number of capacitors, like COM drives get the required capacitance level or value.
Yes.
Then you can
So
adjust
right
that
now,
into your GDS. Yeah.
correct. That's right. So here in this case, we are trying to do the file that I am showing you is purely AC based simulation, that is frequency analysis. In this case, you will not see any output of capacitance. Okay, these are just combs which will show you the frequency response. Let me show you the output of this.
Oh.
For this, I have designed this for a 15 kilohertz. There is a document for this to learn this. So between 12 kilohertz to 18 kilohertz with 2000 number of points in the log scale is what I want to run the simulation, and I get a resonance curve for this. And this is purely a AC based, that is, I'm trying to find the natural frequency of the device.
Okay.
So we call this approach as a top-down approach because we are trying to design from the top view of the device, and then we can convert this into a layout file or a FEM file directly. Okay, I have selected all of them. In this, I go to results and I can see MEMS 3D visualization as an output. So here I need to detect the resonant frequency. So I automatically detect. And we have mode 1, back and forth, looping it. I'm just increasing the scale just for visualization purpose. So this is mode 1. This is mode 2. Okay, so this is how we can do a element-based modeling simulation output also. And this was purely this was purely a frequency-based analysis. I can perform a transient analysis. In this, I give the input signal as pulses. So here I give voltage AC source. And this frequency. And then we perform a transient based simulation. I think I've selected all by default, all the pins I've got selected. Probably that would be the reason why it's taking that long time. Yeah, no, I think this was fine. So this is X, LX, linear displacement, that is in the X direction. This is in the Y direction, and this is in Z direction. And this Rx is the rotation that is seen, okay, in the Y direction and in Z direction. Can always extract these data by double click on this, and then we can extract the data. The advantage of using this element-based modeling or the macro model simulation is, look at the transient simulation number of data. It's about 10,000 number of data. That is 10,000 data points. Consider this to be generated using FEM simulation. It will take a week's time to complete the simulation. 10,000 number of data points. Okay, so what we recommend is, if you are keen about dynamic simulation, then please perform either element-based modeling or perform a macro model simulation output, and then get the dynamic simulation done within a simple module using the macro model simulation methodology. Because with the time, on the time scale, the more the data, more the number of data that we have better clarity, and to generate that in FEM will take a long time, extremely long time. Okay, and if it slips somewhere due to whatever failure mode or what simulation is interrupted, we have lost everything. Okay, so I would recommend, or we would generally recommend, to use this module for dynamic or time-based simulation analysis. Okay. Yeah. Okay.
So you can start sharing your screen, Dr. Raja,
Yes.
and
Yeah,
continue with the session.
yes. Yeah. Sure. Yeah. Okay. I think most of it is what I have already covered. Let me show you one more example of element-based model simulation, where we have 3 plate elements, and we have an element called beam to gap. So let's look into this detail. So we have this element, and this is our focus, and it has a capacitance symbol between them. So this element can generate the capacitance, meaning it can calculate the capacitance in the simulation. So here, this is a case where we have a structure like this. Let me show you the layout file of it. So here it's a serpentine suspended structure. Okay, and equivalent, we can also see the 3D model of it, just for understanding purposes. So this is what we are looking at now. So it has 3 plates, 1, 2, and 3, which are connected. And sorry. So here we have these, just for visualization purpose, we are not using this model to perform any FEM analysis. Okay, so here, this is the model that we have, and we can perform a transient simulation on this one. So where are the inputs that we give? Let's go to the full file information. Whenever we connect a plate element is connected only when there is a inertial device that is in play. So usually inertial device works on a principle of frame of reference. Okay, here we have this global frame of reference. In this case, we are not directly feeding in an input or the load to this device directly. Instead, we are feeding it to this element. What are we feeding? We are feeding in y direction a acceleration of 49 meter per second square, which is 5g. Okay, and then with this, when we apply, what is the typical capacitance that it can generate? It generates is what we are trying to simulate. So now we select the signal of interest. So wherever we connect this element, these are the points. So we are trying to get the capacitance of the bottom plate on one side, the top plate on the other side. So we have two-sided capacitance. So here I'm trying to extract is this side of the capacitance and this side of the capacitance. Similarly, this one and this one. So we get 4 discrete capacitance output. So let me run the simulation. So here we have this displacement of the device with respect to time. So we also have the capacitance of the bottom of both sides and the top of both sides. So now I get this, but I have a problem. The problem is, as a device, this has to give me one capacitance value. But in this case, I cannot take from 4 different input, and then how do I calculate? For that, we have something called as wave runner. Wave runner is a graphical a tool where we can play with the data generated by plotting various types of graph. So in this case, we add the signal. So here we will see with respect to time, we can get the capacitance output. So here we have, right? In such cases, what we do is to plot the overall. All 4 can also be plotted on. So this is what we have, the 4 capacitance value. So here it's obvious that one side, when there is a yeah, so you have a question, Kadir?
Yes, Sripad. So I think these are the non-differential capacitance you are measuring even through wave runner. Can we
Yes.
do the differential capacitance, like if the comb drives are moving in y direction? So where the gap is closing, we have more capacitance, and on the other side, where there is a distance between the 2 fingers, so the capacitance
Correct.
is less. So if we do the differential, how we can do that if we want to measure the differential capacitance?
Yes. So for that, what we do here is I need to add up all these signals, right? So whenever there is a pull, when there is a deformation on right side of the accelerometer, then the capacitance on the left is less because the overlapping area is low. Same way, on the left side when it is pulled, the right side, the capacitance is low because the overlapping area reduces. So there is always a balance that happens between with respect to time. So for that, this is the overall capacitance that we have right now. So if we zoom here, so this is what we have, right? So now what we do is, yeah, so we can do some log, semi-log, FFT, convert this to time to frequency. So these are some things that which I'll not cover now. However, what I can do is add something called add a new signal. With respect to time, I want to add the bottom side of the capacitance. The bottom of one side, the bottom of the other side, and I will say that it is bottom side capacitance, and I want to perform an mathematical operation of component y plus z. And I check it, and then I add it as a new signal. I repeat the same thing for top side capacitance, and then I name it as top cap, and then I repeat y plus z. I'm just adding the signal. Okay, and then y plus z. Add a new signal. Now, what I have is the total bottom side capacitance and total top. Okay. Now, if I plot this in a graph, this is what I have. Okay. Now I need to add bot and top. So all the four signal gets added. Total y plus z. Check. Add a new signal. Total with respect to time. So this is my differential capacitance that I have from the device.
So it's in farad.
Yes.
Okay.
Oh, sorry. Oh, sorry. This F represents femto.
Femto. Okay. Small f.
Yeah.
Okay. Okay. Yeah.
Yeah. So I just zoom this, and this is what I have. I can export this to a Excel file. Copy. I can always paste this. Okay, so this operation can be done. So I can play with the signals now. So element-based modeling, yes, can really be handy, but I would still recommend users to use the multiphysics approach because it is universally accepted. Okay, so these are some things that will just add some boosters to us, just to verify, just to play around and do some quick calculations using these element-based models. Okay.
So would you comment on that? Would it be easy more for it's like lumped element modeling when we are designing accelerometer or gyro? So for initial design, if someone needs to know the spring constant, number of the comb stripes, the fingers, the capacitance,
Yes.
And then one can design 2D
Yes.
layout based on that.
Yes. Yes.
Oh,
Typically, inertial devices are easy to run on element-based models because it consumes a lot of time on FEM.
agree. So we
So
can replicate
what?
here the
Yes.
like mass spring system also. Or
Yes, that's right.
it
That's
is
right.
this. Okay.
So we recently have this um, document created. So here what we do is the element-based models that are created here can easily be converted to a VHDL file. Mentor, sorry, I think it is fast engine. Yeah, prepare VHDL. So I can convert this to a VHDL file. And how do we further do some simulations? And the physics behind it is what this documentation talks about. Okay, so I would recommend any users who are working on AMS, analog and mixed signal design, to really look into these modules because they may not be interested in MEMS designs simulation, but integrating MEMS with a signal conditioning system can always be an interest. Yeah. Okay, so we can always help to give the information that are required as a part of the support. Yeah. Okay. So I think whatever I had in mind regarding the day 3, I think I'm done as of now. In case if we have to summarize all the 3 days a session, I think we can do that now. Or we already have the overview done by Suraj in the beginning. I think we can also leave at that point. So, Suraj, I have a thought in mind, which probably we can discuss a little later of how do we engage the users in the beginning. Because definitely once they start dirtying their hands with the tool, uh, the real support comes into picture.
Yeah, sure. You can discuss that later. But
Yes.
thank you so much for taking the session today, Dr. Raja. So, would you like to recap just like over the 3 days, different,
Yes.
just give an overview of the different features or aspects of the tool for the participants? And in the meantime, I would encourage all the attendees today to, if they have a question, they can drop it in the chat while Dr. Raja is doing the recap.
Yeah. So let me go back to the installation directory. So here, this is the installation path of the software. Day 1, we learned how to use IntelliSuite software to create 3D models and perform multiphysics simulation based on the physics of the problem. And the approach of the design was to create direct 3D models and then pushing them to analysis modules. Here, the modules are different. The design modules cannot be used for multiphysics simulation and vice versa. So that's why you see so many modules here around. So with one UI, you can do one job. 3D Builder is one UI where you can create 3D structure alone. You cannot perform multiphysics simulation, for which you need to push that to thermo-electromechanical module. Okay, so this is what we learned. And the challenges of using a 3D builder when we have multi-layer geometry can be a challenging in the beginning stage. it's not that we cannot use 3D Builder at all for a multi-layer devices. It's just that we have to abide to the rules of FEM, finite element method. The first rule is we need to have the mesh line or the common node point aligned for the geometry to have a proper mesh line. So in such scenarios, we may spend a lot of time designing them. Instead, I recommend is to use the module called Blueprint, create a 2D layout, import that in 3D, and then push it to thermoelectromechanical analysis. And this is what was covered in day 1 of the session, where we create geometries, the MEMS devices, without the process simulation methodology. We just create CAD models and then we perform the FEM analysis. And in FEM analysis, we explored based on the physics, that is thermal, electrical, mechanical, and coupled devices, what all the simulations that can be performed. And in that interest, we covered what is called as static simulation, dynamic, and frequency based simulation. Static is one input, one output, or a DC based input where the input is a constant value, or a constant value with not changing with respect to time. Okay, so a constant value that is given to perform static analysis. Frequency analysis is carried out to identify the natural frequency of the device. Third one, the dynamic analysis, is to understand the time response of the device for the stimuli produced or to the input load that we have given. So these were the things that were covered on day 1 for various devices. Okay, so even now I can take a pause on day 1 relating to that. In case if you have any questions, I can take a pause, or you can drop your question on the chat box as well. Okay, and moving on day 2, we focused more on clean room simulation. So in the case of clean room simulation, we started with how to import or export or to create layout files using the Blueprint module. Okay, and we integrated the layout with the process recipe in IntelliFab, and then we saw how the lithography and etching activities happen. Okay, that is purely from the device specific recipe, MEMS device specific recipe. In addition to that, we also explored some standalone simulations like ion beam lithography, and I think I can share some of the videos which may consume a lot of time. I could not run some of the standalone simulations in the interest of time, but I can always share it to CMC, which can be shared internally to you. So those are some standard standalone simulations that was explored. And we also moved on to a module called IntelliEtch, where we do a dedicated wet etching simulation of silicon and quartz by user defined orientation. That's the novelty of this module, where we are not doing simulation only for standard plane orientations. It's a user defined orientation 201, 234. So it's purely a physics driven simulation output, which is validated with experimental data. We also run some of the examples like the AFM tip, and I showcased a few examples like the micro needle using the FEM, using the wet etching. How do we achieve such simulations? And those are the tutorials which are available in the installation package. Okay. And further, we saw about I think we discussed more few things on how do we extract the etch rates of the from the SEM images, the SEM images. If you are using a silicon wagon wheels to optimize your wet etching parameters. Okay. Yeah, so this is what we discussed specific to clean room based simulation on day 2. And today we started from a point where we assumed that to we are ready with our device, and our device has to talk to other ROIC for the and for better communication for the users to in the readable format. So in that process, we I explained you how the reduced ordered model simulation is carried out in FEM module, and then we moved on to simple, that is the system model extraction, system level simulation tool, where we load the FEM on a template called the macro model template, and then we connect uh, the input load and further any other circuitry part of it that are essential or that may be required by the users. And we uh, repeated the simulation of FEM on the Lagrangian model, that is the SME, system model extracted model. In case if we are keen about 180 nanometer or 90 node or 65 node technology, how do we take the MEMS device into other EDA tools? I showed the way to do that. That is through the EDA linker. We can convert the MEMS device with two Verilog A VHDL files and any PSpice, Samtrix, .c, MATLAB, Simulink also. So you can convert that, and then we can open that file in other EDA tools. Okay. And further, the nanometer based circuit of ROIC can be designed in other EDA tools. Okay. And further, we moved on to element based modeling. As beginners, if you want to do some quick simulations, you can use this module. However, if you are keen on dedicated simulations like FEM, then I would always recommend FEM simulation because it is universally accepted. These element-based models are definitely gives you better accurate results, but I'm not sure how the reviewers, the peer reviewers would take this. If it's FEM, it's universally accepted. However, there is a feature that we can use it to run some quick simulations. Okay. And yeah, I think this is what the 3-day session was all about. So it was just a showcase event of how to use the tool. Definitely, when you start using it, you will get to know the real pain of using the tool. This is the case everywhere, and that's where we shall get connected and start using it. And for all of you to start with, every module has plenty of examples. Like in the case of TEM, based on the physics, you can select various examples to understand how the simulation settings are done. So in this case, how to do the simulation settings, everything is explained in great detail. So I would suggest you to explore these documents in by yourself, and then you can always link it to your simulation. Yes, Kader.
Apart from these tutorials, do you have any video tutorials or any
Video
other?
tutorials, we do not have it officially, but unofficially, I had some time long ago. I created some of the videos and put them on the YouTube. Uh, I mean, this was just on the personal front. It's available on YouTube. People can use that video tutorials.
Okay, thank you.
Yeah. So in case if there are few simulations that we have done. So after the video tutorials that was created, it has helped me. The support was much better optimized.
Okay, there is a question in the chat box.
Yes.
So it's a question from Luca. Could you give us some advices for beginners? For example, when you show the help documents inside the software was amazing. If you have other advices like this will be very good.
Okay.
So he wants to know some other examples for
Yes.
the
So if you are a beginner,
documents, yeah.
If you are a beginner, use this document, something like this. Please remember the path. This is the installation directory, training application note. So this example, this folder, sorry, let me, not this, documentation, application notes. Yes. So in this case, it's a capacitive microphone. Let me take an example. So what's a capacitive microphone? From the introduction, it starts, and then how the process recipe is defined, and then how do we create layouts, and the process file can be open, and then push that file to a TEM, and then we set the material properties, and then we perform the simulation. So as beginners, I would suggest to use this approach or use these PDFs to start working on, because it really handholds you to do that. Once you are familiar with to a certain level, then you can always explore these modules, because these are specific to the physics of the problem. Okay, if you directly jump into the physics of the problem without without the hands-on on the software, it's not a nice thing. Okay, so this is my advice. So you please refer to all of these examples, repeat them, and please remember that you need not create all of these files, whatever is there in the documentation. If you are a good learner or a quick learner, you can always do that. However, there are files already available in these. So Gyro files are already available. You can just start learning them from there itself. Tweak to some parameters, perform the simulation, learn what's the output. So don't spend more time to do things by yourself in the beginning stage, because it might take a long time to do it. But anyways, it's up to the users how they want to learn it. So this is a hand-holding document of how to create this schematic gyroscope. So you can see that we pulled elements like this, then connected them like a circuit, and then we created this geometry or this structure. So this is a handholding document. Similarly, other simulation devices are also there.
Do you have something on accelerometer?
Gyro is more towards accelerometer, except that if we don't give Coriolis force, then I think you can consider this as accelerometer.
Okay.
Yeah. Other than that, I have created one document for one of the users long back, which I can share there. There it talks about the accelerometer, the one which I showed you just now. I prepared a document on this example. I can share that. So that's an accelerometer.
Okay, thank you.
Thank you, Dr. Raja, for the detailed recap. So anyone else has any questions, please feel free to unmute yourself and ask the question. I don't think we have any more questions, Dr. Raja. So
yes.
Yeah.
Okay.
Thank you
Yeah.
so much for your time over these 3 days and joining us from all the way in India across
Thank
time
you.
zones.
Yeah.
Must be really
Thank you
late
very
for
much.
you.
That's fine. It's always get to it gives me a excitement to connect with all the users who are beginners. We were also in the same stage at once upon a time, and that's how we have come through a long way here. What one thing I would like to suggest all the participants is quickly get in touch with the CMC and start accessing the tool.
Yeah.
And will definitely give you a better support to one thing is for sure that we will not solve your problem, but we will help you to use the tool so that you can solve your simulation problems.
Yes, that's a really good advice, Dr. Raja. And of course, as soon as the tool is available for download through CMC,
Yes.
all of the participants and registrants for the training will be notified through email. So please be rest assured that in the coming few days, you will get a notification in your email where you will have the link to download the tool if for free. Of course, if you are a CMC Academic subscriber. And please get your hands dirty, as Dr. Raja mentioned, with using the tool. You can always fall back to the tutorial that will be uploaded on the CMC's YouTube channel as well. And thank you everyone for your participation today.